So, yeah, we are here to for the week 9 online interaction session. So, I will discuss assignment 9 of the previous year's course. I hope my screen is visible.
Yes, sir.
Okay, thanks, Shalini. So, let's begin. Mm, Week 9, and we are going to discuss assignment 9 of 2021. Okay, so let me just paste the question. So here is the first question. It says consider the vector space V, that is R square, and the linear transformation, which is just the uh, interchanging of coordinates, sending xy to ix, and let W be the subspace spanned by this 1 comma 1. Then W is T invariant. So in the last assignment discussion, we saw that what are invariant subspaces of uh, this V, T invariant subspaces of V, if you remember the questions, because we were in search of some modules, and those some modules were in one correspondence with the T invariant subspaces of this space. So the space spanned by 1 comma 1 was one such space. So I hope you remember that. So it's just saying that W is T invariant. So we have already checked it, and we can define an Rx module structure on the quotient space v quotient W via this. The polynomial px multiplied with v plus W will give you the polynomial in linear transformation pt operated over v plus W. So T is a linear transformation on V, so it's from V to V. So PT is also a linear transformation from V to V. So PT will take V to an element of V. Okay, so PTV is an element of the vector space V. So the map is defined in a well manner. So we need to check that which of the following is equal to this. Okay, so do you want to give it a try? I hope
Yes, sir.
okay, the question is clear to you, the map. The- Okay, maybe we can try together. So
Yes,
it's
sir.
okay. So have you seen this kind of questions before?
नो सर, इस वाली असाइनमेंट में तो नहीं थे ये जो इस वीक की है।
Okay, well, exact question तो नहीं होगा, but similar to this might be.
नो, ऐसा तो नहीं था। होमोमॉर्फिज्म वगैरह के थे।
ओके ओके ना, आगे वो क्वेश्चंस आएंगे, बट ठीक है, दिस काइंड ऑफ लीनियर algebra questions are also nice to see, because linear algebra is an important component of all your competitive exams. So it's saying I equal to 0 to 10. So this is a polynomial. Okay, this is basically your px, and it is multiplied with the element of v plus w, and that element is 2 comma 1 plus w, and as per the definition you will get pt applied on v plus w. So this is px. We need to put t wherever your x is. So I equal to 0 to 10 minus 1 I, that is ti, and this polynomial, the entire polynomial applied on V plus W. This is the definition. Now, as it is just the sum of linear operators, so you can take the V inside. So that will be summation of I equal to 0 to 10 minus 1 I Ti V plus W. Okay, till now I think it's clear.
सर 2, 1 plus W आया.
Uh, yes, yes, yes. I haven't put the value of V. So ठीक है, ये 2,1 आ जाएगा यहाँ पे. So it's 2,4. So it's 2, comma 1, 2, comma 1. Okay. So now we need to see that what is Ti of 2, comma 1 first of all. So what T does with I think I hope my screen is not visible now, right?
Yes, sir.
Yes. So that window has been crashed. Let me reopen it. Okay. So now it's back. It's visible right now. Hello.
No, sir.
Uh,
Yes, now visible.
okay. Thank you. Let me just adjust. Okay. So yes, we were looking at what does this T do with an element. So see, T is just interchanging of coordinates. So let me pick an arbitrary element. What T does with x comma y, it just give you y comma x. Okay, as per the definition, you can see. Okay. Now, if you take a t one more time, that is t square x of y, what it will do, it will just give you t of t x comma y, that is t of y comma x, means you will get your element back. Okay.
Yes, sir.
So what does this says, that t of I x comma y is x comma y if I is even and t of I x comma y is y comma x if I is odd, right? So let's just put this in the curly bracket and get back to our situation. So what does this implies? Let me just copy this and paste it here. This implies that this element was equal to this, right? So now put the values of Ti. So you break it into even and odd parts. That is equal to summation of um, say I equal to 0 to 5 minus 1 raised to 2i t of 2i 2 comma 1 plus w. I have just taken the even parts at one side. It is I of 0, means t of 0, t square, t4, t6, t8, and t10 plus the odd part. So odd part is I equal to say 0 to till 4 it will go minus of 1 2i plus 1. At I equal to 0 you will get 1. At I equal to 4 you will get 9. So this will be t of 2i plus 1 2 comma 1 plus w. Is this step clear?
Yes, sir.
Okay. So that is the most crucial step. Rest things should be okay. So what you have when the index is even, that is when t has even powers. First of all, this minus 1 of 2i will be just 1. T of 2i 1 is identity, right? We have already seen plus w. That's what we saw here. The T of I is identity is if I is even, and it is just the interchanging operator if I is odd. So you will have this plus summation of I equal to 0 to 4 minus 1 raised to some odd number, that is minus 1 times T of 2i plus 1, that is odd. So it will interchange it, that is 1 by 2, sorry, 1 comma 2 plus the. Okay, we are adding the same thing here 6 many times. I equal to 0 to 5. How many indices you have? 6. You are adding the same thing. So it will be summation uh, 6 times 6 times 2 comma 1 plus w, right? And here you are adding 5 times, minus will be common, minus of 5 1 comma w 1 comma 2 plus w. ठीक है? Because v plus w and u plus w is what? V plus u plus w, right? So you can just add them at the level of vectors. So is this step clear?
Yes, sir.
Okay, now just take them together. It is 12 comma 1, oh sorry, uh, 12 comma 6 minus 5 comma 10 plus w, that is 7 minus 4 plus w. Okay, so is this an option? Yes. Okay, so you can look at it once. If there is any doubt, just let me know. Otherwise, we will move to the next question. Okay, I hope it's clear. So,
Yes, sir.
okay. So I will just paste the next question. This question is going to be interesting because we haven't done these kind of things before. So it says let F11 be a finite field of 11 elements and consider the vector space uh, of F11 n, means it's just the n column vectors with each entry in F11, and then V is an n F11 module via A dot V is just A multiplied with V. So let's first understand the module structure. So your ring is the matrix ring over the field F11. Each entry of this matrix is from F11. It's each entry is an n cross n matrix. Now, and your underlined space is the space of n column, uh, space of n column vectors. Okay, so space of n column vectors is group, is an abelian group under addition, and then the scalar multiple is defined like this. You just multiply the matrix with the vector. It's an n cross n matrix. It's going to be an n cross 1 matrix, so the multiplication is okay, and you will get, see, what I mean to say, this is an n cross n matrix, and this is an n cross 1 column vector. If you multiply, as this n is same as this, so this multiplication is allowed, and the final output is an n cross n vector, right? So this vector is inside your space again, so the multiplication is well defined, and you can check that it forms a, uh, it gives you a module structure. Okay, now the question is, how many module homomorphisms are there from V to V? Okay, so any guesses, Shalini? Any rough guess? This is not an easy question, I can understand, but ठीक है, कोई तुक्का मारो. No.
नो सर, तुक्का नहीं मारना।
ठीक है. So see, the entire space of these column vectors is generated by your mm, you can write it as a, okay, let me first define certain matrices. So uh, I hope you know this matrix eij. Eij is just an n cross n matrix with 0 everywhere, and uh, except at I comma j place. Yeah, let me write it mathematically. I think that will be good. So it's a matrix where you have 0, let's say this matrix is some aij matrix. Then you have aij to be, okay, how to write it?
Sir, we can write it as eij is 1 if I equal to j, or and
Mm-hmm.
0 if I not equals to j.
No, it's not like that. So let's say the matrix is your AKL, okay, and EIJ is the name for that matrix. Okay, so what you have AKL to be 0. Yeah, first of all, let me write AKL is equal to 1. If you have K equal to I and L equal to J, and AKL is 0 elsewhere. So it has one only at ijth place, and I accept all other except that place, it is zero. Okay, so uh, now see what you can do now. Let's say your the vector vi is of this form. It is 0, 0, 1, and then 0, 0, and this 1 is at ith place. So after multiplication, what you get if you multiply this, just a second, if you multiply say eij with v of k, what will you get? Let me just try, let us just try with some silly examples. So say your uh, mm, ij is just 1 2. Okay, so it will be just uh, 1 at second place of the first row, and it is 0 elsewhere. And what you want here, let's say I'm putting 1 at the first place. So what will you get after multiplication? Yes, Shalini? uh,
Zero matrix.
yes, zero matrix. ठीक है, so यहाँ था E12, here you have uh, V1, so you get zero matrix. ठीक है, and ये आपको मिल गया zero. और उसके बाद if you want, uh, let us go with V2. so अगर यहाँ पे हम सेम इसके साथ जाएं, 0 0 0 0 0 0 0, then 0, you have say V2, then what will you get here?
One at first place and elsewhere zero.
Yes. Okay, so and let's try with one or two more uh, examples. So let's try to choose something from different from 102. So it is 0 0 1 0 0. Now what will be the answer? Yes,
Zero.
0. Okay, so now I think you can guess it. So eij is mm, vk if j is equal to k, and it is 0 0 vector if yeah, just say elsewhere. Or I just made a mistake, it should be vi. Okay, see here it was v2, v e12. So as your 2 was not same as 1, so you get 0. Here it is e12 and it is v2. So what you got, you get v1. ठीक है, here it was again e12, you multiplied it with v3 and you get 0. So you get an output when this j is same as k, and that output is just v of I. Okay.
Yes, sir.
Okay, nice. So now can you just agree with me on this uh, small observation. Some module generated by V1 is your entire vector space. Uh, is this statement okay? See how it is. You can take EI1, you can multiply it with V1. What will you get? You will get EI, right? Oh, sorry, VI. Agree?
Yes, sir.
अभी देखा ऊपर. uh, and if you take some alpha times eij, if you have some alpha here, so what will you get? You will just get alpha times the output of this. So if you have alpha times e12, then it will be just alpha 000, right?
Yes, sir.
Okay. So and you have, if you have alpha times ei1 multiplied with v1, you would have got alpha times vi, and any uh, v belongs to v. Yeah, let me just write it like this. Let v belongs to v, then v is just uh, sum of alpha e vi I is equal to 1 to n, right? For some alpha e in your f11, the underlined field, because any v you pick, it's going to be a column vector. Then you can write it as a sum of scalar times the sum of these column vectors vi's, right?
Yes, sir.
So, and alpha I vi we have already seen, that is nothing but summation of I equal to 1 to n alpha I e I1 v1 dot. Okay. Now, as it is a module, so you can take this sum inside, and it will just be I equal to 1 to n alpha I e I1 dot v1, right? So each element of v is just a scalar multiple of your v1. So this, the sum module generated by v1 is what it is. It is just the collection of all scalar multiples of v1. So the sum module generated by v1 is v. Agree?
Yes, sir.
Okay, nice. So now why we did all these things? Because let phi be a Uh, now we come to the original problem that says count the number of uh, module homomorphisms from V to V. So let phi be a Mn F11 module homomorphism, be a Mn F11 module homomorphism, morphism from V to V. Then for any V in we have phi of v to be just phi of summation of alpha I e I1 I equal to 1 to n dot v1, and as it is a module homomorphism, so you can take this scalar out. Your scalar is in this case is matrices. Okay, matrices from mn f11. This is a scalar as far as we are considering the module structure, so you can take this scalar out, and this is phi of v1, right? So what you get, that the image of v1 will determine the image of all other elements. Okay.
Yes, sir.
Okay, great. So uh, this implies phi of v1 will give us, yeah, instead of will, let me just write it like this. It is enough to determine phi of v1 for determining phi. Now what your phi of v1 can be, that only thing we need to see, and for all possible values of that, we will get a homomorphism and the question will be completed. So let your phi of v1 is, it's going to be a column vector again, because it's a module homomorphism from v1 to v1. So let it is a1 a2 sum an, where your ai is from f11. ठीक है. So can you restrict some values of ais, or you think that it's going to be the final? See, if this is the final answer, then how many choices you have? For A1, you have F11 choices, A2, you have F11 choices. So it will be 11 raised to n, number of module homomorphism. Or you think that somehow we can cancel some values, and maybe we can get smaller, we will have a smaller number of module homomorphisms. Which idea? No? ठीक है. So we will again go back to our uh, best friend, that is our eij. What it will do, see, we have e of mm, let me just think for a while, just need it to be, let's say, okay. mm, ठीक है. So e of I comma 1, I1 dot v1 is v1 again, right? Or
Yes,
vi,
sir.
sorry, it is vi. We want v1 here, so we need uh, e1 comma I dot vi. ठीक है. Now this I matches with this I, so you will have this one. Or if you are confused with the notation, let me just write j in place of I, because we were following eij notation. So e 1 comma j dot vj is v1. ठीक है? So now you have been given what is, you have assumed some value of this phi of v1. So what does this imply? This will imply that phi of e1 comma j dot vj is phi of v1. But as you are assuming it to be a module homomorphism, this is nothing but your e1 comma j dot phi of vj. ठीक है?
Yes, sir.
Okay. So but you can directly determine what your phi of vj should be by the use of uh, your phi of v1. We have already seen that how you can get an phi of v once you have phi of v1. So just instead of v you put vj. Okay, so what does this imply? That your phi of vj is nothing but uh, here you have just a single uh, index, that is j, because it is v is just a sum of, you are assuming v to be a sum of alpha I vi, right? So you have just j index here, so it is just v vj. So all indices are 0 except the jth index. So you will get from here or let me just take it from here, some arrow. So you will get from here that it is only the jth index survives, e j1 dot phi of v1. ठीक है शालिनी, it's a very crucial step. So did you get it?
Sir, please repeat it once.
Okay, so v was your summation of alpha I vi. So we, if we have vj, that means all alpha i's are 0 except alpha j, which is 1. ठीक है?
Yes, sir.
Okay, so with the help of that notation, we get phi of v, that is summation of alpha I ei1 dot phi of v1. So your alpha I is 0 for all values of I except at jth place where it is 1. So you just have uh, only the jth index remains, and that for that index is I equal to 1 to n. For that index, the alpha is 1 here. So it is 1 dot e j1 dot phi of v1. ठीक है? For all other indices, it is 0.
Yes,
Now,
sir.
okay, good. So, but what is your e of g1? You know this matrix very well now. So e of j1, it is just multiply e j1 with, first of all, this scalar multiplication is like that. So what is e of j1? You have 0 everywhere except at the j1 place. So let's say this is your uh, 0 0 0 0. After that you will have some 1 here, and then again this string of 0 rows will continue. We will have 0 0 0 0 dot 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 0 0 0 0. Okay, so you have 1 only at j comma 1 place. When it is multiplied with your uh, phi of v1, phi of v1 you have already assumed to be something that is a1, a2, so on to an. Then what will you get, Shalini? Uh,
We get AJ at J.
yeah, you will just have aj and rest entries are 0. Good. So that will be your output. Now, mm, with the help of that, okay, we computed what is this. Let me just cut this portion and I will write it again in the next page. Okay. So, okay. So now you have E1j, ij is E1j dot Vj is V1. Phi of E1j dot Vj has to be phi of V1. But as it is a module homomorphism, okay, this is because phi is a module homomorphism. So you can take this scalar outside, and what will you get? You will just have this E1j dot phi Vj, but that you have already seen what it will give you. Phi of Vj is, it is just uh, 0 0 0 0. At jth place you will have 1, and it is 0 elsewhere. Okay, and phi of Vj was, you have aj and rest entries are 0, right?
Yes, sir.
Okay. Mm, just a minute. I'm doing anything silly? ठीक है. What will you get after multiplying it? You will have aj
AJ
here.
at first place.
Yes. And rest entries
0.
0, right? And that has to be same as your phi of v1 from here, right? Just taking it from here. And but your phi of v1, what you assume? It was a1, a2, so on to an, right? So what does this implies? This implies aj is a1 for all j, because your j was arbitrary, right?
Yes, sir.
So your phi of v1 now is a1, a1 or a1 for some a1 belongs to f11. ठीक है?
Yes, sir.
So earlier we have f11 raised to n choices. How many choices are there now?
11.
Yes, 11 choices. And now it's up to you to check that for each choice of a1 you will get a module homomorphism. A1, if you take a1 to be 0, then it's just a 0 morphism, right? Because phi of v will be what? Phi of v is just scalar multiple of uh, phi of v1. If phi of v1 is a 0 matrix, then it's just 0, uh, multiplying it with a 0 matrix, you will again get a 0 matrix. So for a1 equal to 0, it's a module homomorphism that is trivial. But for all other values of A1 also, you will get a module homomorphism. You can try with smaller numbers also. Like instead of trying for F11, you can go for F2 and just see if 0 and 1 for two choices you are having two morphisms or not. Okay, so now
Yes,
it's a
sir.
check. I am leaving it to you that for each value of A1 belongs to F1, you have a module homomorphism. Okay, and that will imply that there are 11 uh, MNF1. This 11 should be written as this, but otherwise it will have you will have confusion. 11 MNF1 module homomorphisms from V to V. Okay, so this question
Yes, sir.
itself has taken the entire time. Okay, so let me. Do you need a quick review, or you are okay with whatever is going on?
Okay, sir.
ठीक है. So let us move to the next question then. So next questions are not that much tricky. So I will just give you some hint, and I think you can capitalize on that. ठीक है. For example, this question. Change the page. The third one. It's asking for true or false. Given a ring R and a left module M, consider the submodule P of M. Then there exists Q such that Q submodule of M such that P direct sum Q is M. So what it says that for each submodule of R module M, you are always you will always get a, complementary module. So I will say that the statement is false because you can take the ring to be Z, M also to be a Z. Z is a Z module. Everything is a module over itself. So now what you need a sum module. Take P to be 2Z, right? And let there exist Q such that P direct sum Q is M. Then what you will have? Uh, you want some. First of all, Q has to be non-zero because 2Z is not same as Z. So at least you need to add something, right?
Yes, sir.
So let some uh, small q belongs to Q, and that is something non-zero. Then Q plus Q. What is the addition in integers? It is just the usual addition. This 2Q will also belongs to Q, right?
Yes, sir.
But as your P is 2Z, this will implies that 2Q also belongs to Q, P, and that will implies that P intersection Q is non-empty,
Yes, sir.
and this will contradict to the fact that this sum is a direct sum.
Yes, sir.
So the statement is false. ठीक है. Okay, so let me go to the next question. Okay, ठीक है. So it says that let n greater than n be a composite number, then the z module, z modulo, and z can be written as a direct sum of two non-trivial sum modules. So what do you think? Is it always true? Any guess? Okay, so let me tell you that this is not true. You can take any number which is of the form p raised to n. So the smallest such number is 4. Okay, so then what is this z modulo and z? It has 4 elements, and those 4 elements are the cosets of 4z. One coset is 4z itself, then you have 1 plus 4z, then you have 2 plus 4z, and then 3 plus 4z. It is basically just the group uh, z4, right?
Yes, sir.
Okay, so you can see that the module generated by 1 plus 4z is same as the module generated by 3 plus 4z, and that is the entire z4z, and the module generated by 4z is nothing but the trivial sum module. Okay, so um, it is saying that as a direct sum of two non-trivial sum modules. So the only non-trivial sum module of z mod 4z is the module generated by 2 plus 4z. That is, it has two elements, 4z and z plus 4, 2 plus 4z. Okay, so let's say you can write it like that. Let z modulo 4z is uh, mm, direct sum, but for direct sum you need both the intersection should be uh, different, right?
Yes, sir.
Okay, so this itself implies, but z mod 4z is not equal to the module 2 plus 4z direct sum with 2 plus 4z. Okay, so that means the statement is false. ठीक है, so
Yes, sir.
let's move to the next question. Next question will take some time. The question itself is a bit lengthy. Okay. So it says that R is the ring of polynomials in X, and X and let A is the ring of polynomials in independent interminutes. Just consider it as a ring in infinitely many variables, T1, T2, so on. Okay. Define an action of R on A as follows. So 1 dot f is 1 is f again, no problem. For any n greater than 1, this xn will act on 1 and it will give you tn. 1 is an element of this A. So when xn, which is an element of R, is acting on this one, it will give you tn. And xn of acting on ti is ti plus n for all I greater than equal to 1. Now, if f is a monomial of degree at least 2, so monomial is just when you have product of variables like t1, t2, or t1 squared, t2, like you have more, it's just a polynomial with a single term. Okay, is the definition clear?
Yes, sir.
Okay, so if f is a monomial of degree at least 2, then define x dot f to be 0. See here, these are all not, these are monomials of degree 1. Ti is a monomial of degree 1, the highest power is 1 in Ti. Okay, but if you have some, say, Ti square, then x acting on that Ti square is 0, or you have T1, T2, that will also x acting on that will also be 0. So any monomial means a single term of a polynomial which has degree more than 1. X acting on that will give you 0. Now this can be extended z linearly, because for each term of the polynomial you have defined the action, and then you just extend it with addition, and that will give you an action of R over the entire space A. Okay, and then you need to check that this action give you an R module, because see, after multiplying an element of R with an element of A, you are again getting an element of A. Okay, here you are just defining an action by x i's, but say if you have say x1 plus x, uh, say it's just a polynomial in one variable, so you have x plus x square. You want to check its action over f, so you are supposed to extend it linearly. Just first check, uh, let me just write something. What does this mean by linearly? By linearly, it means that, say you have x plus x square, it is capital X in their notation. So just check x dot f plus x square f and take its addition. Okay, so you have to extend it linearly. Now in f also, it's a polynomial. We are defining action over monomial. So let's say it is of this kind, t1 plus t1 t2 square, or t1 t2 like this. Okay, then you just distribute it over this dot operation. That's what they are telling you. You extend it linearly, and you know that x dot t1 is what, and x dot t2 is what, and x dot t1 t2 is what. Similarly here also you need to extend it linearly. And that gives you an action, a scalar multiplication. Okay, is the definition clear?
Yes, sir.
Okay, great. So now there are two statements. First statement is, Uh, the map phi from R to A defined as phi R to be R dot 1 is a R module homomorphism. The map phi from R to A defined as phi R dot 1 is a ring homomorphism. So you can, so let us see which statement is correct or which statement is not. This is also an interesting question. Okay. So let us first pick two elements. Let uh, this R is from the ring R, which is a polynomial ring in variables X. So we are supposed to take the polynomials. So let me denote one polynomial by, say, capital P. P is summation of AI x raised to I equal to 0 to n. This is a polynomial, and q is summation of I equal, or if you want we can go with some other index, j equal to 0 to m b j x j. Both these are inside your R. ठीक है, both are polynomials in one variable. So we need to check uh, uh, that whether p plus q distributes, uh, or phi of p plus q is phi of p plus phi of q. That is the first condition over for module homomorphism, right? Is this true?
Yes, sir.
So what is phi of p plus q? This is, so phi p plus q is summation of k equal to 0 to n c uh, k x, oh sorry, n plus m, just poly multiplication of polynomials xk, where this ck is just a minute, it is n plus m, where this ck is the summation of uh, till k, some other index I need, so maybe l equal to 0 to k, you have ak b k minus l, oh, al, ठीक है. This is how we multiply to polynomials, right? uh,
Yes, sir.
ठीक है. So now we want the image of this. So its image is just summation of k equal to 0 n plus m ck xk dot 1. That's how this morphism is defined, r dot 1. And for 1 you have that xn dot 1 is tn, right? So they said that we have to extend the above relations linearly. So we can write simply, this is same as summation of k equal to 0 to n plus m ck times xk dot 1. Now what is xk dot 1? This is just tk, ck and tk. Oh, not tk, t of k, the kth indeterminate, right? xk dot 1
Yes,
was
sir.
tk. ठीक है. So now let us check what is phi of p plus phi of q. Phi of p plus phi of q. So it was phi of summation ai xi I equal to 0 to n plus summation plus phi summation I equal to 0 to m bi xi. ठीक है. So that is summation of I equal to 0 to n ai xi acting on 1 plus summation of I equal to 0 to m. Oh, so we have made a silly mistake here. This is not multiplication, this is addition. शालिनी आपने भी नहीं बताया. So
Sorry, sir.
ठीक है. So we need to assume that something is bigger and something is smaller. So let without loss of generality, let you have n greater than m. ठीक है. तो अब ये मल्टीप्लिकेशन ये कैसे होगा? ठीक है, आई थिंक आई डोंट नीड टू रब ऑल these things. n तक जाएगा ये, n is greater, n is greater, and ठीक है, ck will be ck is ak plus bk if k is less than equal to m, and it is just your ak if k is greater than m. Agree? Because after m you won't have a coefficient of b, right?
Yes, sir.
Clear है या you're just saying yes?
अब क्लियर है सर। वो
It's
ऊपर
just
पहले वो वाला मुझे समझ नहीं आया था, मल्टीप्लिकेशन। आई थॉट कि मुझे ही नहीं आता वो, शायद इसलिए मैंने यस बोल दिया कि बाद में क्लियर कर
okay.
लूंगी।
इट जस्ट प्रोडक्ट, वो यहाँ प्लस की जगह डॉट होता है, देन प्रोडक्ट ऑफ पॉलिनोमियल्स, वैसे ही होता है, राइट? तो यहाँ तो इट्स जस्ट एडिशन ऑफ पॉलिनोमियल्स, सो यू जस्ट नीड टू टेक द लीनियर सम
यस
कोफिशिएंट.
सर।
ओके, ठीक है. सो ठीक है, नाउ फाई ऑफ पी, फाई ऑफ यू हैव दिस, you have bi dot xi dot 1. So again, you can extend it linearly in all these things. Same argument will work, and you will have I equal to 0 to n ai ti plus summation of I equal to 0 to m bi ti. So same polynomials. There you have different powers of x. Here you have different variables, but the nature of sum is same. So it will be just here only two pages. Yes. So it will be just summation of I equal to 0 to m ai plus bi of ti, and then you have summation of uh, I equal to m plus 1 to n uh, ai ti. ठीक है. One more thing, why we should restrict n greater than 1? We can also take n greater than less equal to m. ठीक है. So you can see that this is same as phi of p plus q, because here you have summation of k equal to 0 to n ck tk, where ck is ak plus bk if k is less than equal to m, and if k is greater than m you have just ak. So it preserves the addition property.
यस
Okay,
सर।
now we just need to check the multiplication part, and this addition preservation is same as in both ring homomorphism and module homomorphism. So till now both statements a and b are okay. We just need to check but the scalar multiplication property as a ring homomorphism and as a module homomorphism. That might give you some change. So now we need to check that phi of r dot p is equal to r phi of p for some r belonging to your ring. ठीक है. R, it is an R module homomorphism. So R was the ring of mm, this ZX. Oh my goodness.
सर आर बी a polynomial here and p would be a polynomial in t variables.
Yes, 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 yes. We have done some silly mistake in the above also.
Yes sir, because p belongs to a, p
P
q
belongs to
both
N.
belongs to a, so
Yes,
variable
yes.
should be infinite.
Now there also it's finite sum, but instead of xi, we need to take ti. Okay.
Yes sir।
So that will be from A. Ring of infinite determinants means You have infinitely many variables, but at a time you will consider only finite sum. Okay,
Okay, sir.
so it is Ti, Tj belongs to A, then it will become much easier, I guess. Yeah, it is very easy. I don't know why we were doing all these silly things. Scalar multiplication is not even in picture. It is just T of K, and then you have phi of mm, no. See, the domain is R, right? For module homomorphism.
Yes, sir.
So it will be an element of R.
R.
Yes.
Yes, sir.
ठीक है. Okay. ठीक है. So it is AI XI BJ XJ. ठीक है. So here also you will have P plus 2. This will be XK, and then this will follow, and that is inside A. It is from R to A, so it is giving you an element of A. So that is okay. Mm, yeah. So phi of R dot 1 is a module homomorphism or a ring homomorphism that we need to see. So for module homomorphism, you need phi of Rp, R dot P to be R dot phi of P. But for ring homomorphism, you will need phi of R dot P is phi of R times phi of P, right?
Yes, sir.
Okay. So if you are confused with this dot, then yeah, that is okay, because this dot is for module multiplication. Na? So Rp is a multiplication inside your R. So R is inside R and P is also inside R. Okay. So let me just change the color so that it's uh, looks different from the previous one. Okay. So now let's see this. So R और as क्या करें सेम ही ले लें because you are having Q and R both are elements of uh, capital R. ठीक है. So uh, you can just
Sir, for module homomorphism, we need to check the scalar preservation. Phi of R P equals to R phi of P,
yes
where
yes yes
where
yes
R belongs to ring and that P belongs to the Vovala module.
yeah, but here they are
So
saying
here,
is an R module homomorphism. So R is itself a module over R, and A you have given a R module structure. So the scalars will also come from R.
the scalars comes from R, but the polynomial P, I have confusion.
The
P,
polynomial P, see these scalars are in Z. These are polynomials in
yes, sir.
integers, right? So it is an R module homomorphism means the scalars will come from this ring, the ring of ZX. R is a
Yes,
ring,
sir.
and any ring is a module over itself. Okay?
Yes,
And
sir.
over A, you have given an R module structure. For module homomorphism, what you need that both should be modules over the same ring, right? So they are modules
Yes,
over the
sir.
same ring R. So now you can talk about R module homomorphisms. So your scalar will come from the ring R, and
Okay,
it
sir.
will be a
Means they
polynomial.
are taking R as a module over itself and A as a module. Both are modules. Okay.
Yes.
Okay.
It's not written anywhere, but it's saying that R module homomorphism, you have to check it as an R module homomorphism. So it's underlying that what possible module structure you have over R, the uh, natural one, the multiplication inside ring.
Yes,
Okay.
sir.
Okay. So this scalar will be from the ring R. and this polynomial is already uh, there. So let me just paste. So let your uh, R is this polynomial and P is as above. So now that whatever we did earlier, that product of two polynomials, the same thing here will come, and you will have phi of this we need to check. So this is phi of summation of j equal to 0 to m bj dot summation, oh, xj should also be there, dot summation of I equal to 0 to n a j x j. Now the multiplication of polynomial will come into picture. ठीक है? So that we have already seen, it is summation of k equal to 0 to n plus m c of k x of k. The multiplication in polynomial is defined like that, where this ck is summation of L equal to 0 to k a l b k minus l. Okay, so by definition it is going to be summation of k equal to 0 n plus m ck xk dot 1, and as you are supposed to extend the action linearly, so you can take this inside. This is n plus m ck xk dot 1, and that will give you summation k equal to 0 n plus m ck tk. ठीक है, this is your LHS. ठीक है, now RHS is R dot phi p. RHS, so R is summation of j equal to 0 to m bj xj dot phi of p. Phi of p was, we have already computed it in above, that is this summation of I equal to 0 to n ai ti, summation of I equal to 0 to n ai ti. ठीक है, this is your phi of p. Now you need, as the definition is, you need to extend the action linearly. So you, for each j equal to 0 to m bj, you have to take this xj dot with each of this I equal to 0 to n ai ti. And how this action was defined, xj uh, xj ti was ti plus n, right?
Yes, sir.
Okay, so you will get it for each j. This will be bj summation over I equal to 1 to n ai t I plus j. ठीक है, so now you can check, there is some, this should be m, and when you multiply this you will get summation of, this is same as taking summation over k equal to 0 n plus m Because see, I plus j, indices of I and j will added, so you can replace this with new index, and that will be ck tk. So it's a task to you, that to verify the last relation. Just try to see with some example, and then you will have an intuition that yeah, it's true or not. If you don't get it, you can ask me in the next lecture. Okay, so I equal to 0 to k. This is a, uh, k b, uh, al b k minus n, al b k minus n. Okay, so this is same as your uh, LHS. So that is same as your LHS. This implies phi is a R module homomorphism. Now for ring, we need to check that whether phi of R dot P is same as phi of R dot phi of P. Okay, so for that you already have the LHS, right? This is summation of k equal to 0 to n plus m ck tk, and RHS you need to compute. Let me just write the LHS part. Phi of R, if you compute similarly, it will be just uh, I equal to 0 to m. R and P I am keeping as it is, okay, as this. So phi of P was summation of I equal to 0 and AI Ti. Instead of Xi, you are just having Ti. Similarly, if you take phi of this, instead of Xj, you will get Tj. Okay, so it will be just summation of j equal to 0 to m, I guess. Yeah, j equal to 0 to m bj, xj की जगह पे आ जाएगा tj, and then multiplication inside the ring A. This is summation over I equal to 0 to n ai ti. ठीक है. Now see Shalini, these are it's a polynomial with each term uh, of degree 1, right?
Yes, sir. Will.
ठीक है. You have c you have c naught plus c1 t1 plus c2 t2 plus c3 t3, but do, it won't be a polynomial with each term of degree 1, right?
Sir, please repeat.
See, it won't be. I am just saying. First of all, the same multiplication will no longer help you, because that multiplication was inside the ring R. So that there be the explicit formula that how this CK will look like. Okay. Here you need to multiply them individually. But see, let's say for the zeroth index, here you have B naught, you have A naught here. So the coefficient will be B naught A naught. Then for uh, say when J is 1 and I is 1, if you multiply these, you will get a term of the form T1, T1 is right, T1 from here and T1 from here.
Yes, sir.
Or more explicitly, it's a uh, sum of this form B naught plus uh, B1 T1 plus B2 T2 plus so on to dot 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 Bm Tm, right? And you have to multiply it with mm, A naught A1 T1 dot 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 A n Tn. ठीक है. So this is going to be a polynomial. Oh, I should write as a whole. This is a polynomial whose individual.
Sir, this would be a linear polynomial now in variable t1, t2, and so on.
Nah, it won't be a linear polynomial. That's what I'm saying. This is a linear polynomial. This is a linear polynomial.
Okay, sir.
See, just multiply here. You have b1 t1. It will be multiplied with a1 t1, right?
But sir, degree of each ti is 1, so I think it is linear.
See, just take. Let me just write, and then I will give you some example. It's a non-linear polynomial. That's why that is not same as LHS. So
Okay, sir,
I will
when we multiply t1, t2, then it will become non-linear. Means,
even T1 will give you T1 square, na? That's not a linear term.
yes, sir, yes, sir. Okay, okay,
ठीक है?
got it.
Okay. So that will imply that phi is not a ring homomorphism. So it was a module homomorphism, but it's not a ring homomorphism. Okay. So I hope it's clear. We have a addition part will follow for both, and then scalar multiplication will follow, but the ring multiplication won't be preserved. ठीक है, that's why it's not a ring homomorphism, but it's a module homomorphism.
Yes, sir.
ठीक है. So let me write the next question. So it says E, F, G are sequence of R modules and R module homomorphisms. Consider the following statement. A is A and B are like that. So where kernel and image are these are notation for kernel and image. Which of the following are true? So both of them are true. We need to prove them. Let's quickly see the proof. Yes. So 6 part 1. How this set is defined. U of kernel of a part. V compose U is the set of all means is just the elements of the form Vm such that M belongs to kernel of V compose U, right? Clear?
Yes, sir.
But M belongs to kernel of V composed U. What does this means?
Means V composite U at M is 0.
It says that Um such that V composed U M is 0, right? So can I write it like that? N belongs to image of, we're using Im, right? Small Im. N belongs to Im of U such that V of N is 0, right? If it is belong inside if it is of the form that will imply that it is inside image of U, and if it is inside image of U, that means that it is of the form for some M, right?
Yes, sir.
But what does this mean? This means that uh, this is the set n belongs to image of u intersection with n belongs to kernel of v, right?
Yes, sir.
So this is image of u intersection kernel of v.
V.
Okay, so first part is okay. The second part is a bit tricky, so let me solve that also. It says v inverse image of v composed u is same as, let me first write it. It's not an small statement. Image of v composed of u, that is uh, kernel of v plus image of u. Kernel of v plus image of u. Okay, this sum is just the sum of modules. Okay, the sum of module is just the module generated by their union, or the smallest module which contains both of these modules. Okay,
Yes, sir.
ठीक है. So we need to see that. So now if we prove that kernel of v and image of u are both inside this set, then their addition will also be there inside this set, because this addition is the smallest module containing them.
Yes, sir.
Okay, so how to show that? So before that, let me write a statement. If f from a to b is a module homomorphism, then a is always inside f inverse f of a first, and f inverse of b, maybe a more general statement I can write, because we will require a more general statement. So how to denote a subset? Let's say these are m and n. This is m, this is n, this is a, this is a, this is b, and this is b. So a is a mm, subset of where a is some subset of m, and b is some subset of n. Okay, so it is not difficult to see the proof. Part 1, uh, let a belongs to a, then you have f of a belonging to f of a, right? And inverse of this single element. Okay, here I'm not saying that it's an isomorphism, but you can just look at the fibers, the inverse image, inverse of all possible inverses of fa, right? There may be more than one images, because it's need not be injective, but at least a is there.
Yes, sir.
A is one of the three images of f of a. Okay, so what happens? This a is inside a, and this a is inside f inverse f of a, and this is of course a subset of f of a, right? So that will imply that a is inside f inverse. keep these statements as, in your mind, because that will help you in computing many things on module homomorphisms, and that will be frequently used in these exercises also. Okay, so for the second one, let some b belongs to, and keep this order in your mind, that here first you have f inverse, then f, and here you have f and then f inverse. There is no need to memorize it. You need to relate a and this. So see, from a you send it to fa, and you are pulling it back, then only you will come to a, right? Because a is in the domain and b is in the
Yes,
a
sir.
domain. Yeah, b is in the range. So first you have to pull it back, f inverse b, then you apply f. You can't apply f here because b is in already in the range. Okay, so it's like that. So b is inside f inverse of b. What does this mean? This will implies that b is of the form some f uh, f inverse of d, right, for some d in b. Now just a minute. We need to show that this is inside this, and f of, okay, d is inside this. So see what's happening here. You have some d inside your b, right? This is your b. You are looking at all inverses of it. F inverse of, this is f inverse of t, and then you are applying f over it. This is f inverse. Uh, so where it will go? It will go to d again, right?
Yes,
You are
sir.
pulling, you are taking all inverses of d, right? And then you are sending all these inverses, all these p images again through f. So this entire set will be mapped to d again, right?
Yes, sir.
This b will be inside b, and hence this claim holds. So these two statements, if you have, we have taken a lot of time, so let me quickly finish it. So now it's not a difficult thing to see. So once you have these two statements, yeah, the first one is v inverse image of v. That means v inverse composed v composed of u. This image you need to see. So just from here you have by one image of u contained inside this image of v inverse v o u, right? Because it is take your a to be image of u. ठीक है?
Yes, sir.
कोई डाउट तो नहीं है? I think you are looking all these things for the first time,
Yes, sir.
so it makes sense.
Yes, sir. It makes sense.
Image of v inverse composed of u is same as v inverse composed v over image of u, right? So if you take A to be your image of U, then by the above you will get this. ठीक है? Okay. So that means image of U is inside this. The other part we need to see is the kernel. How the kernel is there. Let's just see for a moment. What we need else that uh, okay, image of U is inside this. Then kernel of V should also be inside this. Okay, so let alpha belongs to, or some small v belongs to kernel of V. Then you have no, kernel, it's not a good notation. Let M belongs to kernel of V. Then you will have V of M to be 0, right? We need to show that V belongs to the image of V inverse. But what does this implies? This implies that M belongs to V inverse of 0, right?
Yes, sir.
And as your 0 is there inside image of V compose U, because for each module homomorphism at least 0 should be there, right? Because 0 is sent to 0 by module homomorphism. So 0 is always there inside any image.
Yes, sir.
So this will imply that M will be there inside uh, image of V inverse composed, so V composed U. ठीक है, and that will imply that kernel of V is inside image of V inverse V O U, and that will combinedly implies that image of, what was the statement given, uh, kernel of V plus image of U is inside. Okay, this one side equality is there. Kernel of V plus image of U will be there inside V inverse composed V composed image of, not just composed. ठीक है, till now does it make sense? Shall we proceed?
Yes, sir.
Okay, so one side containment we have shown. For other side containment, see, let n belongs to V inverse composed V image of U, then your uh, n has to be V inverse composed V times some U of alpha for some alpha inside. What is the domain of U? I think E, right? So inside the domain of U, E. Okay. So now you need to check that V over this N minus uh, U of alpha, that is V over V inverse composed V composed U of alpha minus U of alpha, which is V composed V inverse composed V composed U alpha minus V composed U of alpha. So you cannot write directly it to be 0 because here V inverse is not an isomorphism. ठीक है? But
Yes, sir.
by part B, I think, yeah, part B, uh, part second. F inverse of B. Take B to be the image of this V composed U. ठीक है. By second, you have V composed V inverse of this V O U alpha. This to be inside for this smaller set. Uh, this to be inside the set V composed U alpha. ठीक है. But this set is singleton. Once your alpha is fixed, this set is singleton, right? So two singleton set, one is uh, contain. So at least see this is inside V of U of alpha, and this set is singleton. What does this mean? That your V composed V inverse composed V of U alpha is same as V of U of alpha, right?
Yes, sir.
So that will make this to be V of U alpha minus V of U alpha, the above long term, and that will cancel out and it will give you 0. That will imply that n minus U of alpha is inside kernel of V, and that means your n is inside kernel of V plus image of U, and your n was arbitrary element of that set. So this, hence the equality holds. This implies B is correct. Okay,
Yes, sir.
so just 5 more minutes I will take, and then we will stop. Is it okay?
Yes, sir.
ठीक है. So the seventh question is uh, again the same kind of relations we need to prove, but see your part one is uh, solution. A part is uh, same as, yes, similar to 6b. Here you have both a f inverse f of a plus kernel of f. So if you take a to be image of u, then what it will be? Kernel of, instead of f you have v, kernel of v plus image of u, and here you have f inverse f kernel of uh, just a minute. A is your image of u, so f inverse f image of u, and here you have image of u plus kernel of f. It is exactly same, just a you need to take to be image of u. Okay, so this is same as
Yes, sir.
6b. So I'm not doing it here, it's just a repetition. So second part we will see, and second part is easy to see. So it's the b part. By second above, you already have f inverse v to be inside b, right? And clearly see this is uh, inside the domain of f, so it is f applied on something,
Yes,
right?
sir.
So it will also be inside image of f.
F.
Okay, so it is inside the intersection b intersection image of f. So f inverse of b is inside b intersection image of f. ठीक है. The other part we need to see, let m belongs to b intersection image of f. This will implies that m belongs to b, and M is of the form some Fn for some n inside the domain of f was m. ठीक है, उल्टा लिख दिया notation. Oh, so this is n, this should be m. ठीक है, it is n n m for some m inside m. ठीक है, what does this mean? You from here, what will you get? M is inside f inverse of n,
And
and n is already inside your yes, n belongs to this, and n is equal to this. Sorry. So you need to prove that n is of the form f times yes. ठीक है. So this will implies that f of m, that is your n, is inside f of f inverse of n, right?
yes, sir.
And that means your n is of the form some f times f inverse of something, right? So this will imply that f inverse of b is inside b intersection image of f. ठीक है. So 7a and 7b are also these are questions of same nature, so I don't think there is any you have any problem with that. ठीक है, if you just understand one, then it's just a computation, and those two statements will be helpful to you again and again. So just remember those two statements which I stated in the beginning. Okay, so let's see the
Yes,
last
sir.
question. 2 more minutes I will need. So here there is a new definition. I think you haven't seen it. So it's a very easy definition. It says that if f is a module homomorphism from m to n, then it's said to be essential. First of all, it is if it is injective, and every non-zero module of n, when you take the pre-image of it, it's again non-zero. Okay, so if the module homomorphism you take to be just the inclusion map, and this if this inclusion map is essential, then you say that m is an essential extension of n. ठीक है. Okay,
Yes,
is it
sir.
clear? ठीक है.
Yes,
So we
sir.
need to see that whether r is an essential extension of q, or q is an essential extension of z. Okay, so first of all, r is not an essential extension of q. So from q to r you have the inclusion map. And it is going to be injective because it's an inclusion. The only thing you need to check that whether the pullback of every non-zero submodule is a non-zero. So for uh, a to be the module of this form, alpha times root 2, such that alpha belongs to z, this is a submodule of uh, r, right? But what is the inverse of it? Inverse, you can check that it's going to be 0. Why? Because see what inclusion does. Inclusion just sends q to q, and if you take the pre-image of all other elements, you won't get anything, right? Pre-image of root 2 is nothing, because root 2 is not mapped to anything. Sorry, right?
Yes, sir.
So only pre-image you will get for alpha to be 0. So, and 0, as it is an injective map, the pre-image of 0 will be 0. So the pre-image of this entire set is going to be 0. So this is a non-zero submodule whose pre-image is 0. So this implies that uh, R is not an essential extension of Q. So this implies R is not an essential extension of Q. ठीक है.
Yes, sir.
So then second is Z is an essential, Q is an essential extension of Z. So you need to see the inclusion map from Z to Q and see for any, let A non-zero be a some module of Q, then uh, you can prove that its pre-image is also non-zero. How? And it is a non-zero sum module. Uh, be a non-zero sum module of Q, and let A something non-zero is inside A. Then A is of the form P by Q for some P and Q. Q is a non-zero integer. Q is just an integer, right? But that will implies that A plus so on, because it's a Z module, K many times, sorry, Q many times. What it will be? Add A Q many times,
AQ.
A Q or QA, what it is? It is just P, right? And as you have picked A to be non-zero, so your P has to be non-zero, otherwise A to be zero. This is non-zero, right?
Yes, sir.
And this QA should be there inside your A, because A is there, so it's any times if you take the sum of it, it should be inside A because A is a sum module. So this will imply that P belongs to A, right? And that will imply that I inverse of P, that is P, which will be inside I inverse of A, right? Because P is an integer, so its pullback will be P again. It's injective also, so that there will be one image, but uh, inclusion map का inverse image क्या होगा? It will be just the same element, right? So it will be inside I inverse of A, and P was non-zero, so that will imply that I inverse A is non-zero. ठीक है? So if you pick any non-zero module, its inverse is non-zero, so that means that Q is an essential extension of Z. Is it clear?
Yes, sir.
Okay. So, is there any doubt in any of the question, or I shall stop it here?
No, sir. Clear. Thank you.
ठीक है. Thank you, Shalini. So I'm stopping it here.